we present TaxoAdapt, aligning LLM-based multidimensional taxonomy construction to evolving research corpora. The rapid growth of scientific literature makes organizing and retrieving domain knowledge increasingly challenging. Existing expert-curated taxonomies can't keep pace. Automatic methods either overfit to one corpus or rely solely on the background knowledge of large language models, overlooking how research topics evolve across multiple dimensions. Moreover, a single paper may contribute simultaneously to tasks, methods, datasets, evaluation metrics, and applications. Unidimensional taxonomies hide these cross-cutting relationships. We address these gaps using TaxoAdapt, a framework that dynamically adapts an LLM-generated seed taxonomy to a given corpus and across all core dimensions of research. TaxoAdapt operates on three core principles. Knowledge-augmented expansion produces specialized, relevant taxonomies. Rather than mining isolated terms, we reason over documents, the paper's titles and abstracts, to decide how each paper refines its dimension subtree. Hierarchical text classification supplies signals for exploration. High paper density at a leaf triggers depth expansion. A surge of unmapped papers under a parent signals missing width. Taxonomy-aware clustering groups pseudo-labeled papers into coherent, non-redundant child nodes, preserving granularity and coverage. TaxoAdapt tackles taxonomy construction in three core steps. First, we take an initial seed. We prompt an LLM once to create a single-level taxonomy for each dimension. Step 2 involves multi-dimensional classification. We partition the corpus so that every paper is routed to all of its relevant dimensions. The third step is top-down expansion. We use LLM-based hierarchical multi-label classification to determine a node's density, or how many papers from its parent node are mapped to that node. Density provides us the following signals for triggering expansion. Depth. When a leaf node becomes noticeably overcrowded, we split it up to reveal finer-grained topics. On the other hand, for width expansion, when many papers inside a parent node do not clearly belong to any of its existing children, a high unmapped density, we grow new sibling branches to capture those emerging directions. In order to expand a node with new children, we ask three questions. Does the proposed child belong under the parent? Does it cover the crowded or uncovered papers? And clearly differ from its existing siblings, if any? We incorporate these principles into our expansion step. First, subtopic pseudolabeling. Given the paper's title and abstract, along with its parent's path, we return a brief dimension-aware tag naming its direct subtopic underneath the parent node. This is the pseudolabel. Then we utilize these pseudolabels for subtopic clustering. We group these pseudolabels into clear, non-overlapping topics, each of these topics becoming a new child node. With the new children in place, we send every paper back through the classifier, refreshing our density signals and continuing our expansion process until every node is balanced and well covered, or until the taxonomy reaches the maximum depth. In order to evaluate TaxoAdapt, we utilize multiple datasets spanning more than 7,000 papers from EMNLP 2022, 24, ICRA 20, and iClear 2024. These conferences cover NLP, robotics, and deep learning topics. Against corpus only, LLM only, and hybrid baselines, TaxoAdapt's taxonomies are 26.51% more granularity preserving, 50.41 more sibling coherent, and around 5% more dimension aligned and corpus relevant overall. TaxoAdapt builds balanced, cohesive hierarchies. Baselines often form uneven trees with single-child branches and mixed levels of granularity. TaxoCom, for example, stays too coarse, leading to its high relevance scores but very poor granularity scores. TaxoAdapt, on the other hand, doesn't sacrifice granularity for coverage and relevance, still preserving the hierarchical relationships between the topics of the taxonomy, with cohesive sets of children for each non-leaf node. TaxoAdapt is also very robust to different model settings. Its results, using only an 8 billion parameter open source model, is very competitive compared to the GPT-based baselines, even exceeding our main Llama GPT variant of TaxoAdapt in certain cases. We also conduct a qualitative case study where we visualize the ability of TaxoAdapt to capture research evolution. We illustrate TaxoAdapt's sensitivity to change. In the newer EMNLP 2024 corpus, we observe new branches and nodes for instruction following, adversarial language modeling, and personalized language modeling, along with meaning summarization and code summarization. Earlier staples, like mass language modeling in 2022, recede, faithfully mirroring the field's shifting focus. Overall, TaxoAdapt is a scalable, multi-dimensional, and dynamically adaptive method for organizing scientific knowledge in rapidly evolving domains. Please check out our paper and our code if you're interested, and reach out if you have any questions or are interested in collaborating. Thank you.